There is a question Enrico Fermi supposedly asked over lunch in 1950, and 3 short words have haunted astronomy ever since. Where is everybody? The galaxy has hundreds of billions of stars, most of them with planets, and the math behind the Fermi Paradox has always insisted somebody else should be out there. But 5,000 years. That is the entire span of recorded human history, from the first cuneiform tablet to the phone in your hand, and according to a recent calculation, that may also be the average lifespan of any technological civilization in the galaxy. Which means we are not late to a party that ended, we may be early to one that has not started. Tonight, we are folding time into the Drake equation as a 4th dimension instead of a multiplier, and watching the most famous paradox in modern science quietly dissolve into geometry. Subscribe if you are enjoying the journey, get comfortable, maybe pour something warm, and stay with me. Because once you see what time actually does to this equation, you cannot unsee it, and the silence stops being strange. Part 1. The crack in the question. For 64 years, we have been staring at the night sky and asking the same question, and for 64 years, we may have been asking it the wrong way. The question, of course, is the one Enrico Fermi supposedly muttered over lunch at Los Alamos in 1950, when the conversation drifted toward flying saucers and intelligent life among the stars. He looked up from his plate, did a little mental arithmetic in that famously quick mind of his, and said the words that have haunted astronomers, philosophers, and science fiction writers ever since. Where is everybody? 3 words, a simple question, and underneath it, a contradiction so sharp it has cut through every confident prediction we have ever made about our place in the universe. The contradiction goes like this. Our galaxy contains somewhere between 100 billion and 400 billion stars. Most of those stars have planets. A meaningful fraction of those planets sit inside what we call the habitable zone, that narrow ring around a star where liquid water can exist on the surface without boiling away or freezing solid. Even if you assume that life is rare, that intelligence is rarer still, and that technological civilizations are rarer than that, the numbers are so absurdly large that even tiny fractions of tiny fractions still leave you with thousands, maybe millions of civilizations scattered across the Milky Way alone. The galaxy should be loud. Radio chatter, megastructures, probes, beacons, accidental leakage from 100,000 alien television networks broadcasting whatever the equivalent of a sitcom is on a planet 800 light-years from here. Something, anything. And yet, when we point our most sensitive instruments at the sky and listen, we hear nothing, not a whisper, not a click. Not a single confirmed signal that did not turn out to be a microwave oven in the break room of the observatory itself, which, by the way, actually happened, and is one of the funnier footnotes in the history of science. So that is the paradox. Probability says the galaxy should be teeming with neighbors. Observation says we are alone, and in the gap between those two statements, an entire field of speculation has bloomed. The great filter, the dark forest, the zoo hypothesis, self-destruction, simulation, hibernation, indifference. Every few years, a new explanation surfaces, and each one tries to bridge that gap with some clever idea about why the aliens are quiet, or hidden, or already gone, or never were. But what if the gap is not a real gap at all? What if the paradox is not unsolved, but misframed? What if the question, the very question, where is everybody, contains a hidden assumption so deeply buried that we have spent 6 decades chasing answers to a problem that does not exist in the form we keep imagining? That is the idea I want to walk you through tonight, and it is the strangest, calmest, most quietly devastating answer to the Fermi Paradox I have come across in a long time. Because the trick, it turns out, is not in the variables we have been tweaking. It is not in the fraction of stars with planets, or the probability of life arising, or the odds of intelligence evolving. The trick is in something even more fundamental. The trick is in the dimension we forgot to count. Where is everybody? Notice what that question quietly assumes. It assumes that everybody, whoever they are, should be findable now. Right now, in this present moment that you and I happen to be sharing as you listen to my voice. The question assumes simultaneity. It assumes that the universe is a kind of gigantic room, and that all the inhabitants of that room are sitting in it at the same time, and that if we just listen carefully enough, we should be able to hear them breathing. But the universe is not a room. The universe is not a snapshot. The universe is a process, an unfolding, a four-dimensional fabric in which time is not a backdrop against which things happen, but a dimension through which things move. And the moment you treat time as a real dimension, the moment you stop pretending it is just a number you multiply at the end of an equation, the entire shape of the Fermi Paradox changes. The intellectual backbone of every Fermi Paradox discussion is the Drake equation. You have probably seen it. It is a string of variables multiplied together, written out by the astronomer Frank Drake in 1961 as a way to estimate the number of detectable civilizations in our galaxy. Rate of star formation, fraction with planets, fraction habitable, fraction where life arises, fraction where it becomes intelligent, fraction that develops technology, and finally a term we will come back to over and over again tonight, the lifetime of a technological civilization. Multiply them all together, you get a number. Big number, small number, depending on what you plug in. For 64 years, that equation has been the lens through which we have looked at the question of cosmic loneliness. And for 64 years, almost nobody has noticed that the equation does something very strange with time. It treats time as a multiplier, as if time were just a knob you turn at the end of the calculation, as if the only thing that matters about the duration of a civilization is how it scales the final number up or down. But time is not a multiplier. Time is a dimension. And when you treat a dimension like a multiplier, you do not get a wrong answer in the small details. You get a wrong answer in the entire structure of the problem. The missing variable is not missing. It is misplaced. And once you see it sitting there in the wrong slot, you cannot unsee it. The stakes here are not small. If the equation is structurally wrong, then 60+ years of interpretation, 60+ years of speculation about why the aliens are silent may be built on a foundation that quietly tilted to one side a long time ago. Every great filter argument, every dark forest, every zoo, every simulation theory, all of them have been trying to explain the silence by inventing reasons for the aliens to behave a certain way. None of them have stopped to ask whether the silence itself is the strange thing, or whether, given the actual geometry of the universe, the silence is exactly what the math should have predicted from the beginning. Silence may not be surprising, silence may be inevitable, and the path to seeing why runs straight through a shift in how we picture the galaxy. We have been thinking in 3 dimensions. Stars here, planets there, civilizations scattered across a flat map like pushpins on a corkboard. But the galaxy is not a corkboard. The galaxy is a 4-dimensional volume that includes time, and once you draw it that way, once you actually let time be a dimension, instead of a footnote, the empty sky stops being a mystery. It is not a distance problem, it is a dimensional problem. I want to be careful here, because this is not a doom and gloom video. This is not a video about how we are all alone and the universe is cold and meaningless. The tone I want to keep tonight is the tone of a correction, not a crisis. We are not discovering that something terrible is true. We are noticing that something we assumed was a paradox might just be the most honest answer the universe was ever going to give us, and that the answer has been hiding in plain sight inside an equation we have been writing on chalkboards since the Kennedy administration. So here is the question I want to set on the table for the rest of this video, the question that everything else tonight is going to circle back to. What happens when time is treated as a dimension rather than a variable? What happens when we stop multiplying by time and start moving through it? What does the galaxy look like when you draw it in 4 dimensions instead of 3? And once you draw it that way, where does everybody actually go? Because they have to be somewhere. The probabilities are too large for them to simply not exist. So if they are not here, in this present moment, listening for our signals or sending their own, then they must be somewhere else. And the somewhere else, as we are about to see, is not a place, it is a when. Part 2. The equation that framed reality. To understand why the Drake equation has quietly steered us wrong for so long, we have to go back to the room where it was born. The year is 1961. The location is the Green Bank Observatory in West Virginia, tucked into a quiet pocket of the Appalachian Mountains, where the radio noise from civilization is low enough that the giant dish antennas can listen for whispers from the stars. Frank Drake, a young radio astronomer who had already attempted the first modern search for alien signals just a year earlier, was hosting a small meeting. About a dozen scientists, astronomers, biologists, chemists, a young Carl Sagan among them. The meeting had no flashy title. It was just a gathering of curious minds trying to figure out how to think clearly about a question that, at the time, was barely considered respectable in scientific circles. Drake faced a problem. He needed an agenda. He needed a way to organize the conversation so that 12 smart people did not just spend 3 days talking past each other. So, the night before the meeting, he sat down and wrote out a string of variables. Not because he thought he could solve the equation, not because he believed the numbers were known. He wrote it out because he wanted to make sure every relevant question got asked. The equation was a checklist, a conversation starter, a scaffolding for thought. That is the first thing to understand, and it is the thing that has been most consistently forgotten in the decades since. The Drake equation was never meant to be a predictive formula. It was meant to be a framework, a way of breaking a giant impossible question, are we alone, into smaller pieces that could each be examined on their own terms. Drake himself has said as much many times in interviews and lectures over the years. The equation is not a calculator. It is a way of organizing your ignorance. But here is what happens when you write something down. Once a thing exists on paper, in symbols, with an equals sign, it starts to feel like a calculation. People plug in numbers. People publish papers with their preferred values. People debate which variable should be larger or smaller. And slowly, over decades, an equation that started life as an agenda turns into something that feels like physics. It develops an aura. It carries the weight of mathematical certainty, even when the inputs are wild guesses. So let us actually look at the 7 variables, but I want you to look at them not for what they mean individually, but for what they do as a structure, because the structure is where the trouble lies. The first variable is the rate of star formation in the galaxy. How many new stars are born each year? That is a rate. Stars per year. Already the equation is asking us to think in terms of flow, in terms of something happening over time. The second variable is the fraction of those stars that have planets. That is a fraction, dimensionless, just a number between 0 and 1. The third variable is the average number of planets per star that could potentially support life. Another simple count. The fourth is the fraction of those potentially habitable planets where life actually develops. Fraction, number between 0 and 1. The fifth is the fraction of life-bearing planets where intelligent life evolves, another fraction. The sixth is the fraction of intelligent civilizations that develop technology capable of releasing detectable signals, yet another fraction. And then we arrive at the seventh, the famous L, the lifetime of a technological civilization. How long does a civilization last in its detectable phase before it goes silent, whether by extinction, transformation, or simply choosing to stop broadcasting? Now look at what just happened. 6 of those variables are dimensionless or rate-based. They are pure numbers or numbers per unit time. The 7th variable is the only one with the dimension of time itself. years, decades, millennia. And what does the equation do with this lonely time variable? It multiplies. You take the rate of star formation, multiply by all the fractions, and then multiply by L. The result is, in theory, the number of detectable civilizations in the galaxy right now. Stop and feel that for a moment. Time, the only genuinely four-dimensional quantity in the entire equation, gets reduced to a single number you multiply at the end. As if you could capture the entire arc of a civilization, billions of decisions, millions of generations, the rise and fall of empires, and the slow drift of language and technology, by writing down a single integer next to a multiplication sign. It is like trying to describe a movie by reporting only its runtime, 2 hours and 17 minutes. That tells you nothing about the plot, the characters, the scenes that linger long after the credits roll. It tells you nothing about when in the film the protagonist makes the choice that changes everything. The runtime is a real number. It is a true fact about the movie, but it is not the movie. And if you tried to predict whether two strangers would meet inside that movie based only on its runtime, you would be missing every interesting thing that actually determines the answer. That is what L is doing in the Drake equation. It is reporting the runtime of a civilization without telling you when in the cosmic timeline that civilization played. And because the equation just multiplies by L at the end, it cannot distinguish between a galaxy where 10,000 civilizations all flourished simultaneously last week and a galaxy where 10,000 civilizations flourished one at a time, each one lasting a few thousand years, spread out across 10 billion years of cosmic history. Mathematically, those two galaxies look identical to the Drake equation. Observationally, they could not be more different. In the first, the sky is full of neighbors. In the second, the sky is almost certainly empty, because by the time any given civilization is broadcasting, all the others have already gone quiet or have not yet learned to speak. This is what I mean by snapshot bias. The equation, despite being framed as an estimate of detectable civilizations, quietly assumes that everyone you are counting is alive at the same moment. It assumes simultaneity without ever putting that assumption into the formula. It is a hidden variable, an invisible coefficient of 1, that says all civilizations that have ever existed are for the purposes of this calculation eligible to be detected by us right now. That is a wild assumption, and nobody really argues for it. They just inherit it, because it is built into the structure of the equation. You write n equals the product of 7 things, and you do not notice that you have implicitly assumed that all the civilizations counted in that n are temporally co-located, because the equation never gives you a place to ask the question. So, what does this mean for the central thread of tonight's investigation? It means that if L is misused, if time is being treated as a multiplier instead of a dimension, then the entire equation may be structurally incomplete. Not wrong in the sense that the numbers are off, wrong in the sense that the question being asked is not the question that needs answering. The Drake equation calculates how many civilizations exist now under the assumption that all of cosmic history is collapsed into a single moment. But the universe does not work that way. The universe has a time axis. And until we put time back into its rightful place as a dimension, every estimate we generate from this equation is going to be subtly, persistently, beautifully wrong. And here is where it gets interesting. Because if the equation is structurally incomplete, then the silence we observe is not a paradox at all. It is a clue. It is the universe telling us, very politely, that we have been asking the wrong question. The right question is not how many civilizations exist. The right question is how many civilizations exist within a window of time and space where their existence could overlap with ours. That is a very different question, and it has a very different answer. To get to that answer, we have to confront the assumption that has been quietly running the show this whole time. The assumption that the cosmos has a single present moment in which everyone is supposed to show up. Part 3. The Illusion of Cosmic Simultaneity. There is a phrase I want to introduce here, because once you have a name for something, you can finally see it for what it is. The phrase is cosmic simultaneity, and cosmic simultaneity is the hidden assumption underneath nearly every Fermi Paradox discussion you have ever heard. Cosmic simultaneity is the unspoken belief that when we talk about civilizations in the galaxy, we are talking about civilizations that are alive together, that all of them, or at least the ones we are counting, share a present moment with us, that somewhere out there, right now, as you listen to my voice, there is some other being on some other planet looking up at their own night sky and wondering the same things we wonder. The image is so seductive that we forget it is an image. We forget that we have placed it in our minds, and we treat it as if the universe itself has confirmed it. But the universe has confirmed no such thing. The universe is far older than human civilization, far older than any plausible technological civilization that could have arisen from the chemistry of carbon and water and starlight. The Milky Way galaxy is roughly 13 billion years old. The Earth is 4.5 billion years old. Multicellular life appeared about 600 million years ago. The first hominids walked upright about 6 million years ago. Recorded human history covers about 5,000 years. Radio technology, the kind of technology that produces signals detectable across interstellar distances, is about 120 years old. So when we casually aggregate civilizations across the history of the galaxy and treat them all as potential conversation partners, what are we actually doing? We are taking 13 billion years of cosmic history and squashing it into a single instant. We are pretending that a civilization that flourished 2 billion years ago, when our planet was a barren ball of bacterial slime, is still somehow in the conversation. We are pretending that a civilization that will flourish 2 billion years from now, on a planet around a red dwarf star that has not yet birthed its first complex life, is also somehow available to be detected today. That is not how reality works. A civilization that existed 2 billion years ago is not silent because it is hiding. It is silent because it is not there anymore. Its signals, even if they were broadcast in every direction at the speed of light, have long since washed out into the noise of the cosmic background. Its monuments, if any survived, are buried under continents of new geology on whatever world they once stood on. Its descendants, if any exist, are unrecognizable. The civilization is gone. Time has consumed it. And no amount of careful listening on our part is going to bring it back into a conversation with us, because conversation requires that both parties exist within a window where signals can travel between them within the lifetimes of their senders and receivers. This is the part that breaks the traditional Fermi paradox, and it breaks it quietly. The traditional framing treats time as a kind of currency you can spend in any direction. Civilizations long extinct, civilizations not yet born, all get added to the same balance sheet, all get counted toward the total. But signals do not work that way. Detection does not work that way. Two civilizations cannot interact unless they exist within an overlap window, and that overlap window is brutally constrained by both their lifespans and the speed of light. Imagine a cocktail party. A really big cocktail party. The biggest cocktail party in history. 13 billion years long. Now imagine that each guest at this party only stays for a few thousand years before leaving. Some show up early, some show up late, some are still on their way and have not arrived yet. At any given moment, you can only talk to the guests who happen to be in the room at the same time as you. The party in total may have hosted millions of guests across its enormous duration, but the room you are standing in right now may only contain a handful, or one, or none. That is the galaxy. That has always been the galaxy. We have been imagining a single crowded room where everyone shows up at once. The reality is a 13 billion year long event, where guests arrive and depart on schedules we have no way of predicting, and where the simple question of who is in the room with you depends entirely on when you happen to be there. Time separation in this picture becomes a barrier just as real as spatial distance. You cannot send a radio signal across 1,000,000 years any more easily than you can send one across 1,000,000 light years. In some ways, it is harder. A signal that crosses 1,000,000 light years still has the chance of being received if there is a receiver on the other end at the moment the signal arrives. A signal that crosses 1,000,000 years has no such guarantee. The receiver may have ceased to exist before the signal reaches them, or the sender may have ceased to exist before the receiver was even born to point an antenna in the right direction. So detection requires overlap, not just in space, in time. Both axes at the same time, with both civilizations existing in the right place and the right when, and with the signal having enough time to cross the gap between them while both are still listening. Strip away any one of those conditions and the detection fails. And the more you stack the conditions, the harder it becomes for any two civilizations to ever actually find each other, even if they exist in enormous numbers across the full cosmic timeline. This is what I mean when I say that traditional Fermi thinking collapses the time axis into a single moment. It takes the entire history of the galaxy, all 13 billion years of it, and folds it into the present moment, and then asks why the present moment is so empty. It is empty because we have been confusing the size of the entire party with the size of the room we happen to be standing in. The room is small, the party is enormous. Most of the guests will never share the room with you, and that is not a paradox. That is the geometry of any large event spread over a long duration. Once you see this, the temptation is to keep treating the galaxy as a static map and just acknowledge that some of the dots on the map are old and some are new. But that is still not enough. The galaxy is not even a map at all. Maps are two-dimensional or three-dimensional snapshots. The galaxy is a process, a history, a four-dimensional structure unfolding through time, in which civilizations are not points or dots, but trajectories, lines. Threads moving through the fabric of space-time, appearing somewhere, lasting for a while, and then ending. Most of those threads will never touch each other, not because the galaxy is too big in space, because the galaxy is too big in time. And this is where the paradox starts to dissolve, not into solution, into recognition. Recognition that we have been counting wrong, looking wrong, framing wrong. The civilizations may be there, plenty of them. They may have been there in extraordinary numbers across the full 13 billion year sweep of galactic history, but almost all of them are temporarily invisible to us. They are not hiding. They are not dead in the dramatic sense. They simply do not exist in our slice of the four-dimensional pie. To make this concrete, we now have to step into the dimensional correction itself. We have to put time back where it belongs. Not as a multiplier at the end of an equation, but as a dimension, an axis, a real direction in which civilizations exist and move. And the moment we do that, the galaxy stops being a corkboard and starts being something much stranger, much bigger, and much, much emptier in any given moment. Part 4. The Missing Dimension. There is a phrase that physicists use, casually, almost without thinking about it, that should probably stop everyone the first time they hear it. The phrase is space-time, not space, not time, space-time, one word. Because in the framework of relativity, which has been the best description of how the universe actually works for over 100 years, space and time are not separate things. They are woven together into a single four-dimensional fabric. You cannot move through space without also moving through time. You cannot exist at a location without also existing at a moment. The two are not just related. They are aspects of the same underlying structure. I am not going to drag you through the math of relativity tonight. The math is beautiful, but it is dense, and we do not need it to make the point I want to make. What we need is the picture of the galaxy not as a flat map of stars, not as a three-dimensional cloud of points, but as a four-dimensional volume in which every star, every planet, every civilization has not just a location but a history, a trajectory through time. In relativity, this trajectory has a name. It is called a world line, or, more loosely, a world tube, when you want to talk about something extended in space, like a planet or a civilization or a galaxy itself. A world line is the path an object traces through the four-dimensional structure of space-time. Every moment of your life, every place you have ever been, every breath you have ever taken, plotted as a continuous curve through the four axes of length, width, height, and time. That curve is your world line. It started when you were born. It will end when you die. Everything you are, in the language of space-time, is contained in that line. A civilization is the same kind of thing, just bigger. A civilization is a world tube. It begins at some moment when the first detectable signature of technology emerges, whatever that means for that particular species. It extends forward through time, occupying some volume of space, and it ends at some other moment when the last signal goes quiet, whether by extinction or transformation or transcendence or just plain forgetting. The world tube of a civilization is, in effect, the four-dimensional shape of that civilization's existence. It has length in time and breadth in space, and outside of that shape, the civilization simply is not there. Now picture the galaxy as a four-dimensional volume, billions of light-years across in space and 13 billion years long in time. Inside that volume, we draw all the world tubes of all the civilizations that have ever existed or will ever exist in our galaxy. How many are there? We do not know. The Drake equation, if we believe its more optimistic estimates, suggests there could be thousands, maybe more. Let us be generous and say there are 1 million civilizations spread across the full sweep of galactic history. 1 million world tubes, each one a thread of varying thickness and length, embedded in this enormous four-dimensional volume. What does that look like? Here is the key insight. It looks empty. It looks almost completely empty, because the volume is so vast and the threads are so thin and so short compared to the scale of the volume itself that even 1 million of them would appear like a few flecks of dust in a cathedral. You could fly through this four-dimensional galaxy for a long, long time without ever crossing one of those threads, and certainly without ever finding two threads that happen to be close enough in both space and time to send a signal between them. The shift from a three-dimensional model to a four-dimensional model, from dots on a map to threads through a volume, is not just a fancy way of describing the same problem. It changes the math entirely. In 3 dimensions, when you want to know whether two civilizations could detect each other, you ask whether they are close enough in space. The relevant volume is the volume of the galaxy, which is large but finite, and any two civilizations that exist somewhere in it are at least candidates for detection, if you ignore time. But the moment you add time as a real dimension, the relevant volume is no longer the volume of the galaxy. It is the volume of the galaxy multiplied by the duration of cosmic history. Space-time volume. And space-time volume is enormously larger than spatial volume because you have just added another factor of billions of years to the size of your search space. The threads are not just sparse in space, they are sparse in time. And the combined sparsity, in 4 dimensions, is so extreme that even with millions of civilizations sprinkled in, the chances of any two of them overlapping in both space and time become tiny. This is the dimensional correction. This is what changes everything. Because the question we have been asking, how many civilizations exist in the galaxy, is the wrong question for a 4-dimensional universe. The right question is, how many civilizations overlap with us? Overlap, meaning they exist within a region of space-time such that a signal sent from them could reach us while we are still here to receive it, and a signal sent from us could reach them while they are still there to receive it. Overlap probability. That is the new central variable. That is the thing that actually determines whether we are alone or just feel alone. And overlap probability, as we are about to see, shrinks dramatically when you do the geometry honestly. Think about it this way. Imagine you are throwing dust grains into a swimming pool, and you want to know how often two grains of dust collide. If the pool is small and the grains are large, collisions happen all the time. If the pool is enormous and the grains are tiny, collisions become rare events. Now imagine the pool is not just a three-dimensional volume of water. Imagine the pool is a four-dimensional volume of water, and the dust grains have to be in the same spot at the same time, where the time axis is billions of years long. The grains are still moving, the pool is still huge, but now you have added another whole dimension across which the grains can miss each other, and miss each other. Statistically, they will, almost always, almost forever. The number of civilizations may be enormous. The galaxy may have hosted a vast cosmic carnival of intelligence across its history, but in any given moment, in any given slice of the four-dimensional cake, the carnival is empty. The performers have packed up. The audience has not yet arrived. There is just the empty tent and the wind moving through it. And this is the first version of the conclusion that the rest of this video is going to keep coming back to. Silence emerges from geometry, not from suppression, not from extinction, not from cosmic fear or political secrecy or some great cosmic filter, from geometry, from the simple, stubborn fact that the universe has four dimensions, that civilizations are short, and that the space-time volume in which they exist is so enormous that overlap, real overlap, the kind that allows for actual detection or contact, is a statistical rarity. If the paradox is an artifact of dimensional reduction, of squashing four dimensions into three and pretending nothing was lost, then the paradox is not really a paradox. It is the predictable consequence of asking a four-dimensional question with a three-dimensional tool. And once we acknowledge that, the question becomes not why is the universe silent, but how silent should we expect it to be, given the actual geometry. To answer that, we have to start measuring the threads. We have to figure out how thick they are, how long they last, and what fraction of space-time they actually fill. That is where Act 2 takes us, into the geometry of silence. Part 5. The World Tube Universe. Let us spend more time with this idea of world tubes, because the more closely you look at them, the more strange and wonderful they become. A world tube, again, is the four-dimensional shape of an object's existence. For a person, the tube is roughly your body wide and however many decades long. For a planet, the tube is the size of a planet wide and however many billions of years long. For a civilization, the tube is more diffuse. It might span an entire planet, or an entire star system, or even, in the most ambitious scenarios, a substantial chunk of a galaxy. And it lasts for as long as the civilization remains a coherent thing, before it either ends or transforms into something so different we would no longer recognize it. Now here is what is remarkable. Once you accept the world tube picture, every civilization in the galaxy stops being a dot and starts being a continuous trajectory, a line drawn through the four-dimensional fabric, and the question of whether two civilizations can detect each other becomes the question of whether their two lines come close enough together to allow a signal to pass from one to the other, with both ends of the line existing during the moment when the signal is in transit. This is geometry. Real geometry, not metaphor. The trajectories exist. They are not just a figure of speech. They are the literal four-dimensional shape of the civilization's existence. And whether two of them intersect in any meaningful way is a geometric question with a geometric answer. Picture a short-lived civilization. Maybe it lasts 10,000 years from the first radio transmission to the final silence. In four-dimensional space-time, this civilization is a thin, wispy thread, tens of thousands of years long, in time, whatever its spatial extent, but still very thin compared to the 13 billion years of cosmic history available to it. If you drew the world tube of this civilization on a chart that compressed all of galactic history into a single page, the tube would be a hairline, a scratch, almost invisible. Now picture a long-lived civilization. Maybe it lasts 1,000,000 years. That is 100 times longer than the short one, but it is still a thin thread on the cosmic timescale. 1,000,000 years against 13 billion is still less than 1 part in 10,000. Even a long-lived civilization, by ordinary cosmic standards, is a brief flicker. The threads are thicker, yes, but the volume of space-time they have to fill is so monstrous that even thicker threads end up being lost in the immensity. The thickness and length of these threads matter, because the probability that any two of them happen to come close together depends on how much space they occupy in the four-dimensional volume. Thick, long threads have a better chance of intersecting with other threads. Thin, short threads almost never do. And given everything we know about the difficulty of building and maintaining a technological civilization, given everything we suspect about the various ways civilizations can fail or transform, it seems likely that the average thread is thin, short, wispy, a flicker rather than a beacon. Most of space-time in this picture is empty, genuinely empty, not metaphorically empty, geometrically empty. The vast majority of points in the four-dimensional volume of the galaxy are not within any civilization's world tube, never have been, never will be. The civilizations are sparse in space and sparse in time, and the sparsity in 4 dimensions is the product of those two sparsities. The result is a galaxy that, in any given snapshot, looks almost completely uninhabited, even if its full 4-dimensional history is not nearly so empty. This is what I mean by sparse distribution of world tubes. Even if we are generous and assume there have been millions of civilizations across the history of our galaxy, the space-time volume they collectively fill is a tiny fraction of the total. Most of the galaxy, most of the time, has no detectable intelligent life in it. And the question of whether we, on Earth, in our particular moment, are inside a region where another civilization's world tube comes close enough to ours for detection to occur is a question of geometric luck. For two civilizations to interact, 2 conditions have to be met. The first is spatial proximity. They have to be close enough that signals can travel between them in a reasonable amount of time. The second is temporal overlap. They have to exist at the same time, or at least at times such that a signal sent by one arrives during the lifetime of the other. Now, of these 2 conditions, you might expect spatial proximity to be the dominant constraint. After all, the galaxy is huge in space, and it is huge in space. But here is the unexpected twist. Time overlap turns out to be the harder constraint to meet, because while the galaxy is about 100,000 light-years across, and stars are typically separated by a few light-years, the time axis is 13 billion years long, and civilizations are typically thousands or perhaps millions of years long. The ratio of civilization lifetime to cosmic history is much, much smaller than the ratio of stellar separation to galactic diameter. Time is the bigger desert. Time is where the threads get most lost. This gives us what I want to call temporal filtering. Even before you ask whether 2 civilizations are close enough in space to communicate, you have to ask whether they exist at the same time at all. And the answer, for any given pair of civilizations chosen at random from across galactic history, is almost always no. They do not. They missed each other by millions of years, or hundreds of millions, or billions. The temporal filter is extreme, and it operates on every civilization independently, before any spatial considerations even enter the picture. Even if you imagine a galaxy densely packed with civilizations spatially, with neighboring civilizations only a few hundred light-years apart, the temporal filter still shreds the overlap probability, Because density in space does not help you if density in time is low. If every star in the galaxy hosted a civilization at some point, but each civilization only lasted 10,000 years, then in any given 10,000-year window, only a tiny fraction of those stars would be hosting an active civilization at the same time. The galaxy would be densely populated in total across history and almost completely empty in any single moment. That is the world tube universe. That is what the galaxy actually looks like when you take time seriously. Not a populated city, a historical timeline of populations, most of which have already passed and most of which have not yet arrived. A four-dimensional canvas painted with thin, scattered threads, the overwhelming majority of which never come close enough to each other in either space or time to ever exchange so much as a single signal. It is, in a way, quite beautiful and quite humbling, because it suggests that loneliness in the universe is not a punishment, it is not a judgment. It is just the natural consequence of being a thin thread in a very thick volume. But beauty is not enough. We need numbers. We need to actually quantify how thin the threads are, how thick the volume is, and what the probability of overlap actually works out to be. Because if the probability is small, but not negligible, then we should still expect to find someone occasionally. And if it is essentially zero, then the silence is not just expected, it is enforced. So in the next part, we are going to put numbers on the threads, and the numbers, when they come, are going to be more revealing than even the geometry suggested. Part 6. The overlap problem. Let us put some numbers on the table, not because numbers tell the whole story, but because numbers, in this case, finally make the geometry feel real. The age of the universe is about 13.8 billion years. The age of our galaxy is about 13.6 billion years. The Sun and Earth formed about 4.5 billion years ago. Complex multicellular life on Earth is about 600 million years old. Recorded human history is about 5,000 years old. Radio technology is about 120 years old. Now those numbers, side by side, should already start to feel uncomfortable, because the gap between 5,000 years and 13 billion years is not a gap, it is a chasm. 5,000 years out of 13 billion is a ratio of about 1 to 2.6 million. If you took the entire history of the universe and compressed it into a single calendar year, all of recorded human history would fit into the last 12 seconds before midnight on December 31st. 12 seconds. That is the size of our civilizational footprint on the cosmic timeline so far, and the technological window, the part where we are actually capable of being detected by anybody, is about 3 of those seconds. 3 seconds out of an entire year. Blink and you would miss it. Now imagine the galaxy is full of similar civilizations, each one a 5,000-year flicker, scattered randomly across 13 billion years of cosmic history. How often would any 2 of them overlap just by chance? Well, the math is not subtle. If each flicker lasts about 1 part in 2.6 million of cosmic history, then for any 2 random flickers to coincide in time, you need them to land within the same 5,000-year window. The probability is brutal. Even if there are 1,000 such flickers spread across galactic history, most of them are going to miss each other entirely. They will not just be in different rooms, they will be in different millennia, different geological epochs, different chapters of the universe's story. Use the analogy of flashes in a dark timeline. Imagine you have a black sheet of paper that represents 13 billion years of cosmic history. Now you take a pen and put dots on the sheet, where each dot represents a civilization that exists for a brief moment. Each dot is incredibly small, because 5,000 years on a 13 billion year timeline is incredibly small. Now scatter, say, 1,000 dots randomly across the sheet. what do you see? You see a sheet that looks almost entirely black, with a tiny scattering of dots that are themselves nearly invisible. And the chances that any two dots happen to land on top of each other, or even close to each other, are vanishingly small. That is the time dimension. That is just one of the four. Now you have to add in the spatial dimensions, where the same civilizations also have to be close enough in space to communicate. So the dot has to land in the right time and the right place. And the right place is itself a tiny region of the galaxy. The chances of an overlap are not just small, they are, for any reasonable estimate of civilizational lifetime, almost arbitrarily close to zero. This is what I mean by probability collapse as the time dimension expands. In a three-dimensional model of the galaxy, where you ignore time and just count civilizations, the probability of finding a neighbor scales pretty intuitively with how many civilizations you assume exist. More civilizations, more neighbors. Standard density logic. But once you add time, the probability of overlap stops scaling so linearly. It crashes, because you are not asking how many civilizations exist. You are asking how many exist within a tiny window of time and space such that detection is even possible. And that window is so small that you can keep adding civilizations to your estimate without significantly increasing the chance of overlap. This is the part that breaks the intuition of most people who think about the Fermi Paradox for the first time. They reason, correctly, that there should be a lot of civilizations in the galaxy. Then they reason, incorrectly, that lots of civilizations should imply a lot of overlap with us. But the math does not work that way. You can increase the number of civilizations by a factor of 10, or 100, or 1,000, and the overlap probability does not rise correspondingly because the limiting factor is not how many civilizations exist. The limiting factor is how much of the four-dimensional volume each one occupies, and that occupancy is dominated by L, the lifetime. So we get this concept I want to call temporal sparsity. The galaxy may be densely populated in total. Across all of cosmic history, there may have been an enormous number of intelligent species, many of whom built radios, sent signals, and looked at their own night skies, wondering if anyone was out there. But because each one only existed for a brief moment, the density at any given moment is low. The galaxy, in any single slice of time, looks empty even if its full four-dimensional history is rich. Simultaneity, in this framework, is statistically rare. Two civilizations choosing the same window of time to exist in is a coincidence that requires either many tries, or a much longer L, or both. And as we add more and more L into the equation, we get a counterintuitive result. The longer civilizations last, the more likely we are to overlap with at least one of them. The shorter they last, the lonelier we should expect to be. Overlap probability scales with L. L becomes the dominant variable in the entire equation, not the rate of star formation, not the fraction of habitable planets, not even the probability of life arising. L, the lifetime, the thickness of the thread. And this is where the central thread of tonight's story snaps into clear focus. If L is small, silence is inevitable. Not because civilizations are bad, not because they self-destruct in some dramatic universal pattern, but simply because short threads in a long volume rarely overlap. Geometry, pure geometry. If L is large, on the other hand, the picture changes. A galaxy where civilizations routinely last 100 million years would be a very different galaxy. The threads would be thick enough to fill significant fractions of cosmic history. Overlap would become likely. Detection would become routine. The night sky would be full of signals. So the question becomes empirical. What is L, actually? Not what do we hope it is, not what do optimists say. What does the universe itself imply, given what we observe? Because the silence is data. The silence is itself a measurement. And if we are willing to take the silence seriously, instead of explaining it away, The silence can tell us something specific about the lifetime of civilizations. It can tell us how thick the threads are. And what it tells us, when we listen carefully, is unsettling, not because it is grim, but because it is precise, and the precision points in a direction nobody really wants to look at. Part 7. The paper that flips the equation. Let us turn now to a piece of recent analysis that has been making the rounds in physics and astronomy circles, including a discussion by the physicist Sabine Hossenfelder, who has spent a lot of time thinking about how to invert questions that have traditionally been asked in only one direction. The idea is simple, almost embarrassingly simple in retrospect, and yet it took 6 decades for someone to lay it out cleanly enough that the implications could not be ignored. The Drake equation, traditionally, takes a bunch of inputs and tries to estimate one output, which is n, the number of detectable civilizations in our galaxy. The inputs are the variables we discussed earlier, and almost every variable has wide uncertainty. So depending on what you plug in, you can get n values that range from less than 1, meaning we might be alone, all the way up to many millions. That huge range has been one of the chronic frustrations of the field. The equation does not give you a confident answer, because the inputs are too uncertain. But here is the inversion. What if you do not solve for n? What if, instead, you take n as a known quantity, and you solve for L, the lifetime of a civilization? Because it turns out we know something about n, even if we do not know it precisely. We know that within our detectable range, n is approximately 0, maybe exactly 0. We have been listening for over half a century with progressively better instruments, and we have not detected a single confirmed alien signal. Whatever n is, in our observable bubble, it is very, very small, possibly 0, almost certainly less than a handful. So if we treat that empirical observation as a constraint, and we run the equation backwards, plugging in the most optimistic plausible values for all the other variables, we can get an estimate for L that is consistent with the silence we observe. Optimistic values, meaning lots of stars with planets, lots of habitable planets, plenty of life, plenty of intelligence, plenty of technology. If life is abundant, if intelligence is common, if technological civilizations arise often, then for the silence to be real, L must be small. The civilizations cannot last very long. Otherwise, the galaxy would be loud, and it is not. When you do this calculation, with the kinds of optimistic inputs that proponents of the search for extraterrestrial intelligence have favored for decades, the number that drops out for L is shockingly specific. It is around 5,000 years. 5,000 years. Not millions, not hundreds of thousands. 5,000. Sit with that for a second. 5,000 years is, by remarkable coincidence, the entire span of recorded human history. From the earliest cuneiform tablets in Mesopotamia to the smartphone in your pocket, the whole arc of what we call civilization fits inside 5,000 years. And the math is now suggesting that this might be roughly the typical lifespan of a technological civilization in the galaxy, from the first radio signal to the last, from the awakening to the silence. There is an irony here, so sharp it almost cuts. The more optimistic you are about the inputs to the Drake equation, the worse the implication for L. If you really believe the galaxy is teeming with potential civilizations, then you have to also believe that those civilizations do not last, because if they did last, we would be hearing them. The silence demands a trade-off. You can have a galaxy full of long-lived civilizations, in which case L is large, but the conditions for life are rare. Or you can have a galaxy where life is common and emerges easily, in which case L must be short, because otherwise the universe would be ringing like a bell. This is what I called earlier the optimistic input paradox. The cheerier you are about how easy life and intelligence are, the gloomier the conclusion you have to draw about how long they tend to stick around. There is no way to have it both ways. The silence is a constraint, and the constraint has to be paid somewhere. Now, I want to be clear about the limitations here. The 5,000-year number is not a hard prediction. It depends on the optimistic assumptions, and if any of those assumptions turn out to be too optimistic, the number could shift. Maybe life is rarer than we think. Maybe intelligence is rarer. Maybe technological civilizations are unusual even when intelligence is common. Adjust those assumptions, and L can be larger. The silence becomes consistent with longer lifetimes if you accept that civilizations are also fewer in number. But here is the robust part. Even when you relax the assumptions, even when you give yourself a lot of room to fudge the numbers in different directions, L stays uncomfortably short. You can push it up to 10,000 years, 50,000, maybe 100,000 under certain assumptions, but you have a hard time getting it above 1,000,000 without making the rest of the equation strain in implausible directions. The result is robust to changes in the inputs. L is short, the thread is thin, the flicker is brief. There is a second constraint that drives the same conclusion from a different angle: the signal crossing time. A signal moving at the speed of light takes about 100,000 years to cross the Milky Way galaxy from one side to the other. So even if there were a long-lived civilization out there broadcasting continuously, the signal it sent would take up to 100,000 years to reach us. And we would only detect it if the broadcast started long enough ago for the signal to have already arrived, and if we happen to be listening at the right frequency at the right moment. This means that the relevant timescale for detection is not just the lifetime of the civilization, it is the lifetime of the civilization minus the signal travel time, plus our own listening window. And once you start adding all these temporal constraints together, you get a detection window that is, in most cases, only a small fraction of L itself. Even shorter than the lifetime, even harder to overlap with. Let me bring this back to the central thread we have been tracking. The empirical result, the short L that falls out when you invert the Drake equation, is not just a coincidence. It is exactly what the four-dimensional geometry predicts. Remember, the geometry told us that for civilizations to be detectable, they have to be thick enough threads in the four-dimensional volume to create overlap with us. Short threads do not overlap. The geometry says, given the silence, the threads must be short. And now the inverted equation gives us a specific number for how short: 5,000 years. The threads are 5,000 years long. Two completely different lines of reasoning, the structural geometric argument and the empirical inversion of the Drake equation, converge on the same answer. Civilizations are short. The cosmos is long. The window for two threads to overlap is vanishingly thin. And the silence we hear is not a paradox, not a mystery, not an indictment of our search techniques. It is the direct mathematical consequence of those two facts coexisting. The question now is why? Why would civilizations be short? What is it about technological intelligence that makes it tend toward brief existence rather than long flourishing? And there are a lot of possible answers, but the most interesting one, the one that flows naturally out of the geometric perspective we have been building, is also the most quietly devastating. It is not that civilizations destroy themselves. It is that civilizations stop being detectable. And the constraint that enforces this is not philosophical. It is physical. It is built into the very nature of how signals move through space and time. Part 8. The silent constraint. Nobody escapes. The speed of light is the universe's hard rule. Nothing travels faster. No signal, no information, no influence. And while light itself is unimaginably fast on human scales, on galactic scales, it crawls. A radio signal leaving Earth right now will take about 4 years to reach the nearest star, 26,000 years to reach the center of the galaxy, 2.5 million years to reach the nearest large galaxy beyond our own. Those are not just numbers. Those are walls. They are the temporal walls that enforce loneliness even on civilizations that exist within the same large structures. Now combine this with the fact that radio signals, like all electromagnetic radiation, follow the inverse square law. The strength of the signal drops with the square of the distance. So a signal that is loud and clear 10 light-years away may be barely detectable 100 light-years away and lost entirely in the cosmic noise floor at 1,000 light-years. Even if a civilization is broadcasting powerfully, that broadcast becomes essentially invisible at galactic distances unless it is extraordinarily directed and extraordinarily energetic. And even then, the signal degrades with distance, gets contaminated with noise, and becomes harder and harder to distinguish from the background hum of the universe itself. So we have two physical constraints. One is the time it takes for signals to cross interstellar distances, which can be tens or hundreds of thousands of years depending on which neighbors we are talking about. The other is the rate at which signals fade as they travel, which means most casual broadcasts will become undetectable long before they have crossed the kind of distances that would let us hear them. These two constraints, combined, define what we can call the technological visibility window, the narrow slice of a civilization's existence during which it is loud enough, close enough, and aimed in the right direction to be detectable by another civilization elsewhere in the galaxy. The technological visibility window is, in almost all realistic cases, much shorter than the actual lifetime of the civilization. Consider Earth itself. We have been broadcasting in radio frequencies for about 120 years, but the kinds of broadcasts we have been making, mostly inadvertent leakage from radio and television transmissions, were never very powerful, and they have actually been getting quieter as we move toward more directed and contained communication systems. Cable television, fiber optics, satellite uplinks that beam directly to specific receivers rather than radiating into space. The trend, over the past few decades, has been away from omnidirectional radio broadcasting and toward narrow targeted communication. We are getting harder to detect, not easier. If our trajectory continues in this direction, our technological visibility window may close even while our civilization continues to thrive. We may go silent, in the radio sense, not because we collapsed, but because we got better at communication. We started using fiber optics and lasers and quantum networks, and the wasteful electromagnetic shouting that defined the early 20th century became a quaint relic of our youth. Imagine an alien civilization listening for us. They might catch a brief window, somewhere between 1920 and maybe 2050, where Earth is detectable as a radio source. Before that, nothing. After that, nothing. A flicker of about 130 years, and then we vanish back into the noise. Now multiply this concern across the galaxy. If most civilizations follow a similar pattern, where they go through a brief, electromagnetically loud phase before transitioning to quieter, more efficient communication, then the detectable window for any given civilization may be far shorter than its actual lifetime. Maybe a few centuries, maybe a few millennia at most. And you have to overlap not with the civilization itself, but with that narrower detectable window which makes the overlap problem even worse than it already was. The shift from leakage signals to directed communication has another implication. Civilizations may eventually decide, deliberately, to stop broadcasting. They may conclude that being loud is dangerous or wasteful or simply unnecessary. They may switch to communication methods we cannot detect because we do not yet know what to look for. The dark forest hypothesis, which I do not particularly endorse but which is worth mentioning in passing, suggests that civilizations might intentionally hide because revealing themselves attracts predators. Whether or not that is the actual reason, the practical effect is the same. Civilizations may not just become harder to detect, they may actively work to be undetectable. And then there is the issue of search strategy. The search for extraterrestrial intelligence, or SETI, has been operating for over 6 decades, and in that time it has only been able to scan a tiny fraction of the radio spectrum across a tiny fraction of the sky. The amount of effort required to do a thorough search is staggering. Even with our best instruments, we are like someone trying to find a single specific song by listening to 1 second of one radio station once a month. The chances that we would happen to catch a signal, even if there were one being broadcast somewhere within range, are tiny. Not because the signal is too quiet, necessarily, but because we are not pointing our ears in the right direction at the right time at the right frequency. So we stack the constraints. Civilizations are short. By the inverted Drake equation argument, their detectable windows are even shorter because of the trend toward quieter technology. Signal travel times are immense because the galaxy is huge. Search coverage is sparse because our instruments are limited. Combine all of these, and the probability that we, in our brief technological window, happen to be pointing our ears at the right star at the right moment to catch a signal from another brief technological window across the galaxy becomes vanishingly small. The math demands silence. The silence is what the math predicts. This is what I mean when I say silence is structurally enforced. It is not that there is nobody out there. There may be many somebodies. It is that the structure of physics itself, the speed of light, the inverse square law, the nature of electromagnetic radiation, combines with the structure of civilizational lifespans to produce a galaxy in which detection is almost impossibly unlikely. Even if civilizations are common, they do not communicate with us, not because they refuse, but because the conditions required for communication are so narrow that they are almost never met. We are not alone because no one else is alive. We may not be alone at all, but we are alone in this moment, in this slice of space-time, in this corner of the four-dimensional volume, because the threads of other civilizations have already faded out or have not yet flared up, or are flaring right now somewhere where their light has not had time to reach us. The silence is real, but it is not evidence that we are unique. It is evidence that we are out of phase, out of sync with whatever else is out there. And that, as we are about to see in the next part of this exploration, is a fundamentally different kind of loneliness than the one the original Fermi Paradox imagined. Part 9. The universe isn't empty, it's out of sync. Let us pause and gather what we have so far. We started with a paradox that was framed as a contradiction between probability and observation. We argued that the contradiction was an illusion produced by treating time as a multiplier rather than a dimension. We rebuilt the picture in 4 dimensions, where civilizations are world tubes rather than dots, and we showed that the geometry of a 4-dimensional galaxy makes overlap between civilizations rare, even when the total number of civilizations is large. We then turned to the inverted Drake equation, which gave us an empirical estimate of L of about 5,000 years, consistent with what the geometric picture would have predicted independently. And we examined the physical constraints, the speed of light, the inverse square law, the trend toward quieter communication that further narrow the window during which any civilization is actually detectable. What emerges from all of this is a synthesis that is both simpler and more profound than any of the standard answers to the Fermi Paradox. The universe is not empty. The universe is out of sync. Out of sync. That is the phrase I want you to hold on to, because it captures something that the language of paradox and silence and great filters has missed. It is not that there is nothing out there. It is that what is out there is not here, in the temporal sense. It is somewhere else in time, somewhere else in the 4-dimensional structure, and the somewhere else is just as real as a somewhere else in space. We just have not been trained to think of time that way. Imagine you are at a busy international airport. Hundreds of thousands of people pass through that airport every year. The airport is, in some sense, a place full of people. But at any given moment, in any given concourse, only a tiny fraction of those people are present. The rest are arriving later, or have already departed, or at home, or in another city, or not yet born, or already retired. The airport is busy in total but sparse in the moment. And if you took a snapshot of the airport at 3 in the morning on a Tuesday, you would see a nearly empty terminal. That emptiness would not mean the airport is unused. It would mean you happen to take the picture at a moment when most of its users are elsewhere. The galaxy is the airport. Civilizations are the travelers. Most of them have already passed through, or have not yet arrived. The picture we have of the present moment shows an empty terminal, and we have been staring at that picture for 64 years, trying to figure out why nobody is here. The answer, in the four-dimensional view, is that everybody is somewhere else. Not somewhere else in space, somewhere else in time. This is the temporal misalignment view of the Fermi Paradox. And it is not really a hypothesis in the same way that the Great Filter or Dark Forest are hypotheses. Those are explanations that try to fit the observations to a story about civilizational behavior. Temporal misalignment is not a story about behavior. It is a statement about geometry. It says, given the proportions of civilizational lifetimes to cosmic history, given the size of the space-time volume relative to the size of any individual civilization's footprint within it, the expected outcome is that we, in any given moment, find ourselves alone. Not because nobody is out there, but because nobody is contemporary with us. The contemporaries, if any exist at all, are sparse to the point of being statistical anomalies. Civilizations may be abundant across the full sweep of cosmic time. There may have been many. There may be many more to come. We may be the most recent in a long line of intelligences that have flickered to life and then faded back into the silence of the universe. We may be the first. We may be one of just a handful currently active across the whole galaxy. Any of these scenarios is consistent with the observations. What unites them is the simple fact that whoever else exists or has existed or will exist, they are mostly invisible to us because they are mostly not here in the temporal sense. There is a difference between absence and non-overlap that I want to underline. Absence means nothing exists. Non-overlap means things exist but are out of reach. These are very different states of affairs, and the standard Fermi framing has tended to treat them as the same. Silence as evidence of absence. But silence is also perfectly consistent with non-overlap. It is consistent with a universe full of life that simply does not cross our particular thread. And once you accept that, the paradox stops being a paradox and becomes something else, a description, a condition, a geometric fact. I notice, when I think about this for any length of time, that the emotional flavor of the Fermi paradox shifts. The classical framing carries a kind of dread. Either we are alone, which is lonely, or there is some great filter that destroys civilizations, which is terrifying. The temporal framing has neither of those edges. It is calm. It is not hopeful in a naive way, but it is not dreadful either. It just says, the universe is bigger than you have been imagining. Time is bigger than you have been imagining. And the strangeness of being apparently alone is just the strangeness of being a brief thread in a long tapestry. There is something almost reassuring in that, not because it solves the problem of cosmic loneliness, but because it reframes the problem. The question is no longer, why is nobody here? The question is, given that the universe is structured this way, what does it mean to be one of the threads? And that question opens up a different kind of investigation, one that is less about looking outward and more about looking at our own place in the four-dimensional structure. This is the central thread of tonight's video, and I want to state it as clearly as I can. The Fermi paradox is not a paradox. It is a sampling problem. Once time is treated as a real dimension instead of a multiplier, the silence of the universe becomes the mathematically expected outcome of short-lived civilizations spread across a long timeline. We are not surrounded by nothing. We are surrounded by a four-dimensional volume in which most of the inhabitants are temporally elsewhere, And the strangeness we feel when we look up at an empty sky is the strangeness of being a brief flicker in a long history. Nothing more, nothing less. But that reframe has consequences. Because if we are a brief flicker, then where do we sit on the timeline? Are we early? Are we late? Are we somewhere in the middle of a long history of intelligences? The temporal model does not, on its own, answer that question, but it makes the question askable in a way the old paradox could not. And there are some intriguing arguments, not proven, but worth considering, that suggest we may be early, that the cosmos is just getting started, that the great age of intelligent life in the galaxy may lie not in the past but in the future, and we, here, now, may be among the first to ask the question at all. Part 10. The Early Arrival Hypothesis. There is a model in cosmological speculation that has been gaining attention in recent years called the Grabby Aliens model, developed by the economist Robin Hanson and a few collaborators. Like all such models, it is speculative, and I want to be clear about that up front. This is not established physics. This is a framework for thinking about how civilizations might be distributed in space and time, given certain assumptions about how they tend to expand. But the model is interesting because it produces predictions that align in some ways with the temporal framing we have been developing tonight, and it offers one possible explanation for why we, in our particular moment, find ourselves alone. The Grabby Aliens model starts from a simple premise. Imagine that some fraction of civilizations, once they reach a certain level of development, become expansive. They start to spread outward, claiming volumes of space, transforming the resources they encounter, and altering their environments in ways that would be detectable from a distance. These expansive civilizations grow steadily, forming visible bubbles of activity that spread at some fraction of the speed of light. Whether they are mining asteroids, building megastructures around stars, or just colonizing planets one after another, they leave a footprint that grows over time. In this model, an active Grabby civilization would eventually fill a substantial volume of the galaxy, or even multiple galaxies, with detectable activity. Their bubble would expand until it ran into another bubble, and then expansion would slow or stop along that boundary. From our perspective, looking at the sky, an established network of Grabby civilizations should be impossible to miss. The galaxy would not look like a normal galaxy. It would look like one with substantial portions reorganized for technological purposes. We do not see this. The galaxy looks ordinary. Stars shine the way physics says they should. Galaxies behave the way galaxies should. There is no obvious sign of large-scale astroengineering. So either Grabby civilizations do not exist, or they do exist but have not yet expanded into our region, or, and this is where the model gets interesting, we are early. We are looking at the sky before the grabbing has really started in earnest. The Grabby Aliens model predicts that early observers, civilizations that emerge before the era when expansive aliens have spread widely, should see exactly what we see: an empty sky, an apparently uninhabited galaxy. The model uses some clever statistical reasoning about when, in the history of habitable conditions, intelligent observers should typically arise, and concludes that observers like us, looking at a sky like ours, are most consistent with being relatively early in the cosmic story. Not the very first, perhaps, but among the early arrivals, before the big expansion. This connects, in an interesting way, to what we know about stellar lifetimes. Most of the stars in the galaxy are not stars like our Sun. They are red dwarfs, smaller, cooler, and far longer-lived than Sun-like stars. A red dwarf can sit there burning its fuel slowly for hundreds of billions of years, far longer than the current age of the universe. The era in which red dwarfs host their largest populations of habitable planets is, in cosmic terms, just beginning. The vast majority of habitable planet time in the galaxy lies in the future, not the past. If life and intelligence tend to emerge on planets around long-lived stars, then most intelligence in cosmic history is yet to come. This line of reasoning suggests that the peak era of intelligent life in our galaxy may lie tens or hundreds of billions of years in the future, when the red dwarfs reach their most stable phases of habitability and complex life has had enough time to evolve on the worlds that orbit them. We, around our young yellow sun, in this early phase of cosmic history, may be looking at an empty sky simply because the party is just starting. Most of the guests have not yet arrived. If true, this would frame humanity as an early arrival, an advanced scout, one of the first kinds of civilization to ask the question, rather than one of the latest. And that is a strange thing to consider, because it inverts the usual romantic intuition that we are the latest in a long history of cosmic intelligences. The early arrival hypothesis says no, we are not the latest. We may be among the earliest, and the silence we hear is not the silence of those who came before, but the silence of those who have not yet been born. There are implications to being first that are worth thinking about, though we have to be careful here, because we are speculating now, and the speculation is much less constrained than the geometry was earlier. If we are early, then the choices we make about how to handle our own civilization may matter not just to us, but to the eventual shape of intelligent life in the galaxy. The patterns we set, the technologies we develop, the values we encode into our long-term institutions may persist or echo into the era when the rest of cosmic intelligence is finally widespread. There is a kind of loneliness in being early, but there is also a kind of responsibility and a kind of opportunity. We may be the first of many. We may be writing the rough draft of what intelligence looks like in this galaxy. Now I want to maintain a clearly speculative tone here. The grabby aliens model is not proven. The early arrival hypothesis is one possibility among several. It could turn out that we are not early, just isolated. It could turn out that grabby civilizations do exist but are very far away or otherwise undetectable. The model is a way of thinking, not a verified prediction. But notice how cleanly it fits with the temporal framing of the Fermi Paradox we have been building. The early arrival hypothesis says we are early in the timeline. The temporal framing says civilizations are sparse in time, and that overlap with us is therefore unlikely in any given moment. The two views are compatible, and in fact, they reinforce each other. If we are early, then the threads of future civilizations have not yet started, and our own thread is one of the earliest in the volume. The four-dimensional structure is mostly unfilled in the time direction we are facing. Most of the intelligence that will ever exist in our galaxy lies ahead of us, not behind, and we are looking out at a volume that is, from our temporal vantage point, mostly empty because most of it has not happened yet. This is the central thread again, in a different costume. The Fermi Paradox is not about distance, it is about time, about when civilizations exist relative to each other, about the geometry of overlap in a four-dimensional structure. The early arrival hypothesis is just one version of the temporal answer. It says we are alone now because most of the others come later. The standard temporal answer says we are alone now because most of the others are not contemporary, regardless of whether they came earlier or come later. Both are facets of the same underlying geometry, and both produce the same observation. An empty sky, a silent galaxy, a cosmos that looks, from our vantage point, like nothing has ever happened, when in fact things may be happening, or may have happened, or may yet happen, all over the place. Just not here, just not now, just not in this particular cross-section of the four-dimensional volume in which we briefly exist. Part 11. The strange weight of being early. I want to take a moment to dwell on this idea of L, the lifetime variable, because it is easy to talk about it as if it is a single number, and I have been talking about it that way for stretches of this video, but in reality, it almost certainly is not. L is a distribution, not a constant. There is some statistical spread of how long civilizations last, and the average might be one thing, while the long tail might be very different. When we say the average lifetime is 5,000 years, we are doing the same kind of compression that gets demographers in trouble when they try to summarize a population with a single number. The average tells you something. It does not tell you everything. And in this case, the things it does not tell you may matter more than the things it does. Consider human variation. Some humans live to be 100. Some humans die in infancy. The average human lifespan in a given population is some number in between, but the distribution behind that average is complicated. There are cliffs and plateaus, dangerous decades and stable ones. Childhood is risky. Then comes a long stretch of relative safety. Then risk climbs again in old age. The shape of the curve is not a smooth bell. It is lumpy and uneven, with thresholds that, once crossed, change the probabilities of everything that comes after. The same is probably true of civilizations. The average L might be 5,000 years, as the inverted Drake equation suggests, but that does not mean every civilization lasts exactly 5,000 years and then ends. Some might last only a few hundred years before failing, never making it past whatever the civilizational equivalent of infancy turns out to be. Some might last hundreds of thousands of years, persisting through transformations that we cannot easily imagine, becoming things their founders would not recognize but that still count, in the geometric sense, as the same continuous thread. Think about that for a moment. A civilization that hits some kind of stability threshold may pull away from the average in a way that has nothing to do with luck and everything to do with structure. Just as a human who survives childhood is suddenly far more likely to reach adulthood, a civilization that survives certain bottlenecks may suddenly find itself in a much longer kind of game. We do not know what those bottlenecks look like exactly, because we have only one example to study and we are still inside it. But the existence of bottlenecks is something the geometry strongly hints at. Distributions with long tails almost always have thresholds that, once crossed, change everything. The long tail of civilizational lifetime matters because the few civilizations that make it to the long tail might be the ones we are most likely to detect. A civilization that lasts 1,000,000 years has a thread that is 200 times thicker than the average. Even if such civilizations are rare, their long persistence makes them disproportionately likely to overlap with other civilizations, including ours. This is the same statistical effect that makes old buildings overrepresented in any given city. You walk around an ancient European town and feel surrounded by medieval architecture, and you might think, wow, they really built a lot of these. But what you are actually seeing is the survivors. Most medieval buildings are gone. The ones that lasted are the ones we still see, and they fill our impression of the period in a way that is not really proportional to how many were built. So when we listen for signals, we may be most likely to hear from the longest lived, the senior citizens of cosmic intelligence, the ones who figured out how to keep going, whatever that turns out to mean. They are the ones whose threads are thick enough to overlap with ours by chance. They are the ones who, statistically, dominate the detection probability, even if they make up a small fraction of all civilizations that have ever flickered into existence. If we ever do hear something, the most likely sender is not a civilization like us, fresh out of the radio infancy stage, but one that has already passed through whatever filters lay ahead of us and has been humming along for a very long time. This raises an interesting question about humanity. Where do we sit on this distribution? Are we destined for a short L, fated to flame out somewhere in the next few centuries the way so many civilizations apparently must, given the math? Are we early in our own world tube, with most of our duration ahead of us, looking back from some far future at this moment, as a kind of awkward adolescence we somehow survived? Or are we somewhere in the middle, with as much past as future, halfway through whatever arc we are going to trace before we fade? We do not know. The answer depends on choices we have not yet made, and on circumstances we cannot fully anticipate. But our position on this distribution is not just a matter of curiosity. It is a matter that affects everything about how we think about our own future. It changes how we evaluate risk. It changes how we think about institutions. It changes how we think about the projects we leave unfinished and the ones we never start. If the average civilization lasts 5,000 years, and we have already been around in some technological sense for about 120 years, then we are in the early phase of our own world tube. We have, statistically, a lot of duration ahead of us if we manage to reach the average. But we also have many opportunities to fail before we get there. The early phase of any complex thing is dangerous. Children die more often than adults. Startups fail more often than established corporations. Coral reefs are most fragile in their first years of forming, before they have built the dense structure that protects the colony. Civilizations probably also have higher mortality in their early phases, when their technological capabilities outpace their institutional and ethical maturity, when the tools they wield are sharper than the wisdom guiding the hand. We have invented things in the last century that we are still, by any honest accounting, learning how to manage. The gap between what we can do and what we know how to do safely is larger than it has ever been. That gap is exactly the kind of feature that produces a steep mortality curve in the early phase of any system. This is not a particularly comfortable thought, and I want to be careful not to slip into existential panic, because that is not the tone of this exploration. The geometry we have been describing is calm. It does not predict doom. It just describes the structure within which doom is one possibility among many. We could have a short L, we could have a long L. The equation does not tell us which. What it tells us is that whichever path we take, our path is an instance of a distribution, and the shape of that distribution is one of the most important variables in determining whether the galaxy as a whole ever becomes a loud and crowded place, or remains a quiet and lonely one. We are, in a sense, voting with our duration. Every civilization that lasts adds weight to the long tail. Every civilization that fails early pulls the average down. The galaxy's eventual character is being decided, slowly, by the trajectories of every flicker that ever lights up inside it. There is a kind of philosophical weight to recognizing this. We are not just observers of the cosmic situation, we are participants in it. We are part of the data set that other civilizations, if they exist, would use to estimate L. Some hypothetical alien astronomer, somewhere in the four-dimensional volume we have been describing, may one day try to estimate the average lifetime of technological civilizations using whatever indirect methods are available to them. And our thread, whatever shape it eventually takes, will be one of the data points feeding into that estimate. Our choices, individually and collectively, are contributing to the long-tail or short-tail nature of the distribution. The decisions we make about how to handle our own technologies, about how to manage conflict and cooperation, about how to think about our long-term future, are not just decisions about us. They are decisions about what kind of thread we draw through the four-dimensional fabric, and that thread, once drawn, becomes part of the permanent geometry of this galaxy. That is a strange thing to sit with. The idea that the choices being made right now, in our particular flicker, will eventually be part of the historical record that future intelligences may or may not ever access, but that exists nonetheless. The thread we draw does not unwind just because nobody saw it. The geometry remembers, even when the observers do not. And that, in turn, reframes the original question. We started by asking, where is everybody? We have ended up asking, what kind of civilization are we going to be? The first question was about other people. The second question is about us. And the move from one to the other is not a digression. It is the natural consequence of taking the geometric framing seriously. Because once you accept that the silence is geometric, that it is the expected outcome of short threads in a long volume, then the only question that remains is how to make our own thread as long and meaningful as possible. The aliens are not going to show up and rescue us from our own decisions. The aliens, if they exist, are facing the same kind of geometric loneliness we are, and they are making their own choices about how thick to draw their own threads. This is not a question with a single clean answer, but it is a question that frames the cosmic situation differently than the traditional Fermi framing did. The traditional framing made us spectators, peering out into a silent cosmos and trying to figure out why nobody was talking. The geometric framing makes us participants, recognizing that our own existence is one of the threads, and that the question of whether anyone hears us depends partly on how long we manage to keep humming. We are not waiting for a signal. We are a signal. We are broadcasting every century we last. The fact that intelligence in this galaxy can reach at least this far. In the central thread of tonight's exploration, this is the moment where the question pivots from looking outward to looking at ourselves. Not in a way that abandons the cosmic perspective, but in a way that integrates it. We are not separate from the data set. We are in it. And the structure that determines whether we are alone is also the structure we are helping to shape. The four-dimensional galaxy is not something happening to us. It is something we are part of. The geometry includes our thread, and our thread is still being drawn. There is something quietly powerful about that recognition. We started this video with a paradox that seemed to be about everyone else. We are ending in a place where the most interesting question is about ourselves. About our own L. About how thick our thread becomes. About what we leave woven into the four-dimensional fabric when our particular flicker eventually fades. The cosmos, as it turns out, is not asking us a question we can answer by listening harder. It is asking us a question we can only answer by lasting longer. The question of longevity, not existence, becomes the central concern. Not because existence is solved. We do not know whether we are alone. We may never know. But existence is not the variable we have any control over. Longevity is. And the longer we last, the thicker our thread, the more we contribute to the eventual filling of the space-time volume with the kind of intelligence that future civilizations might one day overlap with, if any future civilizations come along to do the overlapping. Every additional century is a vote for a louder galaxy. Every premature ending is a vote for the silence we have been hearing all along. That is the strange weight of being possibly early. Not panic, not despair, just the quiet recognition that what we do, here and now, in our brief window of detectability and capability, is part of the larger geometry. It does not make us special, exactly. It makes us responsible for our portion of the canvas. We are holding the brush. The four-dimensional volume is waiting to see what shape we draw before our flicker fades. And whether anyone ever sees the drawing itself will still be there, woven into the fabric, part of the long, quiet history of intelligence in this small corner of a much larger story. Part 12. The final reframe. Let us return, at last, to the question we started with. Where is everybody? 3 words, spoken or muttered or wondered for 64 years, in lecture halls and observatories and quiet bedrooms at 3 a.m, when the sky outside the window seems too big to be real. And now, after walking through the geometry of space-time, the structure of the Drake equation, the inversion that gives us a 5,000-year lifetime estimate, the physical constraints that further narrow the detection window, the emerging picture of a galaxy as a 4-dimensional volume thinly threaded with brief civilizational existences, we can finally give an answer that does not feel like a guess. It feels, for the first time in a long while, like an actual answer, not a clever evasion, not a dramatic hypothesis dressed up in equations. An answer. They are not hiding, they are not asleep, they are not dead in any dramatic universal sense. They are temporally distant, most of them, almost all of them, distributed across 13 billion years of cosmic history in such a way that their threads almost never overlap with ours, and ours almost never overlaps with theirs. The galaxy is full of stories, but we are reading only one page of the book at a time, and the page we are on happens to be mostly blank. Turn the page back, and there are paragraphs we cannot read, because we were not yet born when they were written. Turn the page forward, and there are paragraphs we cannot read, because they have not been written yet. The book is enormous. The page is tiny, and we, sitting on our particular page, sometimes mistake the brief whiteness around our text for the whole story. This is the answer the four-dimensional geometry gives us. And it is, I think, a more honest answer than the traditional ones. It does not require us to invent strange behaviors for hypothetical aliens. It does not require us to assume catastrophic filters or paranoid forests or galactic zoos. It does not need civilizations to be cruel or cowardly or transcended into forms beyond comprehension. It just requires us to take time seriously as a dimension, and to recognize that the silence we hear is the natural music of a four-dimensional universe in which civilizations are short and the volume is vast. There is no villain in this story. There is no conspiracy. There is just geometry doing what geometry does, indifferent to whether anyone notices. The phrase that has been hovering over this entire video, the one I want to leave with you, is this. It is not a distance problem. It is a dimensional problem. Once you fold time into the equation properly, once you stop treating it as a multiplier and start treating it as an axis, the paradox dissolves, not because we have solved it cleverly, but because we have realized it was never the right question. The right question is not, why is the universe silent? The right question is, given the geometry, how could it be anything else? And once you ask the question that way, the silence stops being a wall and starts being a window into how the structure of space-time actually works, when you let it work without the human assumption of a shared present moment hovering over everything. The four-dimensional galaxy is not empty. It is just out of phase. Threads of intelligence flicker into existence here and there, exist for their brief durations, and fade out, with the next thread perhaps emerging on the other side of the galaxy, 10 million years later, never to know that the first one ever existed. Two civilizations could rise on neighboring stars, build telescopes, listen to the sky, ask their own version of the Fermi question, and never know that their counterparts had done the same thing, just in a different millennium. The communication that we imagined was possible, the chatter we expected to hear, was always a fantasy of simultaneity. It assumed that everybody was here at the same time. They are not. They never were. They never will be. And that is not a tragedy. It is the structure of reality. It is what reality looks like when you stop asking it to be something else. There is something philosophically expansive about this realization, because it implies that the question we are asking, where is everybody, is itself a feature of the geometry we are embedded in. Every civilization, presumably, asks some version of this question. Every civilization, at some point in its development, looks up at its night sky and wonders why nobody is talking back. The specific words might be different. The math might be different. The cultural framing might be wildly different. But the underlying question, the act of looking up and being struck by the apparent emptiness that is probably universal, and every civilization, if it does the math correctly, may arrive at the same calm conclusion. The silence is geometric. The loneliness is structural. The question is universal, but the answer is the same everywhere, because the geometry is the same everywhere. This is, in a way, a kind of cosmic communion. Not the communion of contact, but the communion of shared experience. Every thread, in its brief flickering, must eventually realize that the other threads, if they exist, are mostly unreachable. Every civilization must come to terms with the loneliness of being a four-dimensional object in a four-dimensional volume that is much, much larger than itself. The question is universal. The realization is universal. The answer is universal. And in that strange way, every civilization that asks the question is in conversation with every other civilization that has ever asked it or will ever ask it. Even though they cannot hear each other across the gap of time, we are talking, in some sense, to all of them. They are talking, in some sense, to us. Not in words, not in signals, in the shared act of asking, in the shared act of looking up. That is a strange kind of company to keep. The kind that does not require presence. The kind that exists across temporal distances no signal could ever cross. But it is real in the same way that any inheritance is real. We inherit the question from the geometry itself, and we pass it forward just by asking it. We are not the first to wonder. We will not be the last. The civilizations that came before us, if any, asked the same question into the same kind of silence, and arrived at the same kind of geometric clarity, or did not, and faded out without ever knowing. Some of them, perhaps, looked at their math and gave up too early. Some of them, perhaps, did the work and came to the same calm conclusion we are reaching tonight, and then went on with their lives, doing whatever civilizations do when they have made peace with the geometry. The civilizations that come after us, if any, will ask the same question into the same kind of silence, and arrive at the same kind of clarity, or will not. Across 13 billion years and 100 billion stars, the question is the universal question, and the silence is the universal answer. The math is the same on every world. The geometry is the same in every direction. The conclusion, for anyone who follows the reasoning all the way through, has to be the same. What does it mean then to live inside this geometry? To be one of the threads in this immense four-dimensional volume? It means, I think, that the search for meaning cannot rely on contact. We may never make contact. We may never hear from another civilization, not because we are alone, but because the geometry does not allow it. And that means we have to find a way to be okay with that. Not a desperate way, not a denial. An actual coming to terms with the fact that the meaning we hoped would arrive in the form of an alien voice on the radio is probably not going to arrive that way, because that way is geometrically improbable. The meaning, if there is meaning, has to come from within the thread itself, from what we do during the brief window of our flickering, from how thick we make our thread, from what we leave woven into the fabric when our particular flicker eventually fades. There is something quietly beautiful about that. The classical Fermi framing made meaning depend on finding others. The geometric framing makes meaning depend on what we do with the duration we have. We do not need to contact anybody to have a meaningful existence as a civilization. We need to last. We need to think clearly. We need to decide what kind of thread we want to be. The cosmos is not asking us to find our neighbors. The cosmos is asking us to be worthy of being neighbors, in case anyone, ever, eventually, manages to overlap with us. That is a very different assignment, and it puts the work back on us in a way that the old framing never quite did. I find this oddly hopeful, not because it solves the problem of cosmic loneliness, but because it shifts the locus of meaning from contact to character. We may never know who else is out there. We may never know if our thread crossed any others, but we can know what kind of thread we are. We can shape that. And, in the shaping, we participate in the larger geometry, contributing our small portion to whatever the full four-dimensional structure of intelligence in this universe ever turns out to be. We are not powerless in this picture. We are not waiting for someone else to validate our existence. We are drawing the line ourselves, and the line, once drawn, is permanent. The geometry remembers, even when no one is watching. The original Fermi question, where is everybody, assumed that the universe had failed to deliver something it had promised. Aliens. Contact. Confirmation. The promise was implicit, but it was there, woven into the way we framed the question. We expected the universe to be populated, in our moment, with neighbors who would prove we were not alone. But the universe never promised those things. The universe just is what it is. A four-dimensional volume vast in both space and time, populated thinly with brief flickers of intelligence whose threads almost never touch. We have been blaming the universe for a failure that was actually a feature of the geometry. The aliens did not let us down. They were never going to be available in the way we imagined. They are, like us, individual flickers in a long history. We are all in the same situation, even though we cannot meet each other to confirm it. The disappointment we have felt for 64 years was a disappointment with our own assumptions, not with the cosmos. So tonight, as you look up at whatever sky you have, wherever you are, I want you to try a different mental model. Do not imagine the stars as a backdrop against which alien civilizations might be hiding. Imagine them as the spatial cross-section of a four-dimensional structure that includes all of cosmic history. The civilizations are there, somewhere in that structure. Behind us in time, ahead of us in time, scattered across the volume in patterns we cannot perceive from our flat present moment viewpoint. They exist, they have existed, they will exist. We just cannot see them because we are looking at one frame of a 13 billion year movie, and the frames before and after ours, where most of the action is, are not visible from where we are sitting. We are not in an empty theatre. We are in a theatre showing one frame at a time, and the frame we are watching happens to be sparsely populated, while the rest of the film is full. The silence is not empty. The silence is full of histories we cannot access, futures we cannot predict, civilizations whose threads pass through different parts of the volume than ours does. The four-dimensional galaxy is alive, just not here, just not now, just not in this particular slice of the larger story. The aliveness is real. The galaxy is, in its full four-dimensional shape, a place of continuous activity. It is just that the activity is distributed in directions we cannot face. We can only face the present. We cannot face the past, except through evidence. We cannot face the future, except through prediction. And the bulk of cosmic intelligence lives, presumably, in those unfaceable directions. And that, I think, is the calm and slightly devastating final answer to the Fermi Paradox. We are not alone. We are not surrounded. We are temporally embedded, like every other civilization that ever has been or ever will be, in a four-dimensional structure where overlap is rare and silence is the geometric norm. The question we have been asking for 64 years is not unanswerable. It is just structured wrongly. Once we restructure it, the answer becomes clear. Once we restructure it, the silence stops being a paradox and starts being the most honest sound the universe could possibly make. The universe was telling us the truth all along. We just needed to learn how to listen to a four-dimensional truth with three-dimensional ears. We started this video with a question: where is everybody? We end with an answer that is also a question. They are out there, distributed across all of cosmic history, mostly invisible to us because they are temporally elsewhere. They are the threads we will never meet, the flickers before and after our own, the civilizations whose existence is real, but whose contact is geometrically forbidden. They are not gone, they are not hidden, they are just not now. And not now is, in a four-dimensional universe, the most common condition any civilization can be in relative to any other civilization. Not now is the rule, now is the exception. And the few exceptions, if they exist, are scattered so thinly that finding one is more like winning a cosmic lottery than receiving a guaranteed package. If we are the first civilization in our region of the galaxy to ask this question and find ourselves alone, then what does that make every civilization that ever asks it after us? It makes them, like us, threads in the volume, brief flickers asking universal questions, inheritors of a cosmic loneliness that is not really loneliness at all, but the natural condition of being a four-dimensional object in a four-dimensional structure that is much larger than itself. We are the older siblings, in some strange sense, of every civilization that comes after us. They will look up at their own skies, do their own math, and arrive at their own version of the same conclusion. They will not know we did it first. We will not know they did it after. But we will be linked by the question, even though we are not linked by anything else. The party is not over. The party never started. In the sense we imagined, the party is happening at all moments and at all places, scattered across the full volume, and any given guest only experiences the small portion they happen to occupy. We are guests. We are at the party. We just cannot see the room because the room is bigger than we ever knew, and most of it is in directions we cannot face. The other guests are real. They are mingling in their own corners, at their own moments, having their own versions of the experience we are having. We just do not share the room with them. We share the building. The building is enormous. The building is the four-dimensional galaxy. And the building is alive in ways our particular room can only suggest, never confirm. So look up tonight. Look up at the empty sky. Listen to the silence, and know that the silence is not absence. The silence is geometry. The silence is the universe being honest about its own four-dimensional nature. The silence is what every thread hears before it fades, regardless of whether other threads exist or not. The silence is the most reliable sound in the cosmos, the one constant signal that every civilization receives, the universal greeting of a universe that is too big in time to gather all its inhabitants into one room. It is not a cold sound when you understand what it is. It is just an honest one. We are early, or we are alone, or we are simply out of phase with everyone else. The geometry does not care which. The geometry just predicts the silence, and the silence is what we hear. And in hearing it, we join the long, scattered company of every other thread that ever heard the same silence and wondered the same thing. We are not separate from them. We are not isolated from them. We are with them in the geometric sense, in the only sense that the universe with its four-dimensional honesty ever permits. No one is here yet,